Okay, why don't we get started? Let's get started. So I have a little bit of a headache today, so some of the times I might wince. I'm not snarling at you. It's other stuff. So let's pick up where we left off, and we'll spend hopefully no more than maybe 20 minutes going through the material for this particular module, but I'd like to spend the balance of today going over MATLAB, how you might implement one of these conditional probabilities that I've been talking about, the so-called filtering probabilities. So where we last left off, oh yeah, so we have some reading. Please make sure you're keeping up with the reading. So where we last left off, we talked about this idea of a random variable. And a random variable, we said, was some measurement over one of your observations. And the motivating example that we gave was a flip, three flips of a coin. And the random variable in this particular case is going to measure the number of heads associated with three flips of a coin. So we carried out that example and we listed out the distribution associated with each of the measurements this random variable number of heads can output. And we looked at the probability associated with each of them and we listed them out both in a Tableau format as well as a graph. And so we have the number of heads from three flips of a coin can be zero many heads, one head, two heads, or three heads, and the associated probabilities with each of those outcomes of the random variable was 1/8, 3/8, 3/8, and 1/8 probability, respectively. And so, of course, if you add these up, these proportions, these probabilities, they sum to 1. So it does satisfy the so-called law of total probability in that the probability of all the possible outcomes, if you sum them together, that equals to 1. So you can have a proper probability uh, mathematically of a random variable. Okay, and so we also gave two examples about the shape of a distribution, and we plotted on the left-hand side the shape of the distribution for the experiment where we flip the coin three times, and we list out along the horizontal axis all of the outcomes of a random variable that measures the number of heads over those three flips. And so we have for 0, it's 1/8. For one head in three flips, it's 3/8. Likewise, for two heads, it's 3/8, and for three heads, it's 1/8. And then we drew another probability distribution, a fictitious one. And in this fictitious probability, we imagined there was another random variable we called y, and y is going to have some measurement of the number of heads. And let's just assume for the sake of argument, which is what we did, that we had 0, 1, 2, or 3 heads measured by random variable y. And for this other random variable, we made the assumption that the probability of each one of these outcomes of random variable y is 2/8. So we have 2/8 for 0, 2/8 for 1, 2/8 for 2, 2/8 for 3. And then we ask the question, if you were going to wager on a game, either the regular fair coin or this other funky coin measured by random variable y, which one would you wager on? And the answer was, of course, we examined that. You would want to or prefer to wager on the coin flip associated with random variable x on the left because you can kind of count on certain values more than others. And there's some quote unquote structure there. And so with random variable y, each one of those outcomes is equally likely. So regardless of which one you guess, you have three ways of getting it wrong. Whereas for our system x, measured by that random variable, if you were to guess one or two, you would be right more than you would be wrong, right? So because of that, you're more likely to be successful making money over the long term if you were to wager on the system described by random variable x on the left versus if you wagered on the system described by random variable y on the right. So that's where we left off. Any questions about this? Make sense? Okay. So let's continue on. And there's a new construct we'll talk about, the so-called cumulative distribution function, or CDF. And sometimes in probability, we're concerned not just about a single outcome. For example, you measure 0 heads or 1 heads for 3 flips of a fair coin. You might be interested in a set of intervals along this number line for the values of x. And in that particular case, in this example depicted here, we have maybe we're interested in the probability of the number of heads we measure being 0 or 1, right? And you can imagine on this curve representing the probability, you're really trying to do is compute the area under that curve, right? You want to sum together each of those events. And so mathematically, let's say you wanted to know the probability that in three coin flips, that the number of heads that you observe is going to be less than equal to 1. So number of heads is a random variable. It's x. It's measuring something over the outcome. So you get a string of 3 characters, heads or tails. And this random variable is measuring the number of those characters in that string that are heads. And you're interested in either 1 or 2. I'm sorry, rather 0 or 1, i.e., is it less than equal to 1? Okay, so that's a perfectly reasonable thing someone might want to know. You know, you roll a die. What's the probability that the die is going to be less than 5? So 1, 2, 3, or 4. And that might be something you're interested in wagering on. So you can compute the so-called cumulative distribution function, or CDF, by just simply summing together all of those values up to and including that particular value of interest. In this particular case, we're interested in less than equal to 1. So we locate our 1 on our graph, and we sum together all those values up to and equal to 1. Mathematically, we'd use our summation symbol. And on the bottom of that summation symbol, we have this index here. And what we're doing is we're saying for all values y is just a variable, that are less than the x of interest, you're going to sum together the probabilities of those values, right? So in this particular case, we say for all values y that are less than or equal to 1, if we were interested in the probability that the number of heads for our random variable was going to be less than equal to 1, right? So mechanically, this is our expression, and this is something you could certainly implement in something like MATLAB quite easily. And because this random variable takes on discrete values, things that are countable, you can use summation to compute the CDF. Mathematically, if we're going to list this out, we call this a CDF function, capital F of x. So x is the parameter to it, and that's the upper bound over which you're doing this summation. From a probabilistic standpoint, you're looking at the probability that our random variable x, so we use the capital when we x when we refer to the random variable, and we use lowercase when we refer to the values that it can take on. So we say the probability that random variable x is less than equal to value little x is going to be the following, right? So the CDF is typically this capitalized F. This is the probabilistic expression, P of big X less than equal to little x. And of course, the mechanical expansion mathematically is our summation. Any questions about this? Does that make sense? Okay. So this looks a lot like the probability of a complex event. If you examine it, when we talked about complex events, even though it's a random variable, we talked about this idea of taking the union of simple events in order to form a complex event. And then we said if those simple events are non-overlapping, right, you can certainly compute the probability of the complex events by summing together the probabilities of the simple events. So in similar fashion, we're doing the same thing, right? Our simple events in this particular case would be our random variable x taking on a value 0, taking on a value 1. And we're just combining them using that same principle that we can add together simple events in order to form probabilities of complex events. Okay, so this is not enough, right? There are other types of events, complex events that we might want to pose. We might want to have intervals. For example, let's say if we were interested for the 3 coin flip example of computing the probability that the number of heads we measure is going to be greater than 1 or greater than equal to 1, less than equal to 2, right? We might want some interval that isn't like from the end coming up to some value. And so we can certainly use the CDF in order to compute that. Okay. So how we would do that, let's first look at it mathematically, what we're doing. And so the CDF says, I'm going to compute the area under the probability curve, if you will, going from the left-hand side up to some upper bound. And when we have this expression for the probability of an interval on the previous slide, we're interested just in this shaded red region, right? And we can use this tool, our cumulative distribution function, or CDF, in order to construct arbitrary regions like we see here from 1 to 2. So here's what we do. We say, okay, well, if I want to isolate this region here from 1 to 2, I'm going to take the entire region going from the left up to 2, and I'm going to take the entire region going from the left up to 1, and then I'm going to subtract, right? And so the CDF gives us the entire region. The subtraction isolates for us that region from 1 to 2. And so probabilistically, how we would say, well, sort of logically as an expression, we might want to know the example that the probability of the number of heads is between 1 and 2, right? Closed interval on the upper end on 2. And so probabilistically would say, what's the probability that a random variable x is greater than some amount a? In this particular case, a is 1, less than equal to some amount b. In this particular case, b is 2, but you can have a and b arbitrary on your interval. So what would we do? Well, we need that first shaded red region. And in this picture, imagine if all of this graph was shaded in red. I have a pen here, so why am I doing that? All of this graph is shaded in red, right? That's would be the first expression, the CDF at point B, and that would represent this entire region here that's shaded red. And then we subtract from it the second expression, which would represent just this region, which is there in green. So you can imagine the whole shaded red region. If I were to place a green triangle over that superimposed, what's left is what remains when we do the subtraction. Okay, so it would be the red region minus the green region gives us back this region of interest for which we want to know the complex probability. Okay, any questions about this? Does that make sense? Yes? All right, so let's move on. Um, we'll cover more of this as the semester goes on, but at this juncture in the semester, we have two types of random variables. One is called a discrete random variable, and the other is called continuous. And it's really important to know the distinction because that's going to impact how you construct these probabilities associated with complex events. For a discrete random variable, the outcomes of that random variable, the range, if you will, like 0, 1, 2, and 3 in the case of the 3-coin flip, in order to compute these CDFs, you use a summation, right? You can use that summation because discrete values are identifiable, and you can put together those complex probabilities by summing each one of those identifiable simple probabilities. Continuous random variables are different. Those values are uncountably infinite. That's for things like temperature or pressure, right? You can't possibly identify the individual real values. If I were to tell you to give me a number between 60 degrees and 61 degrees, you might say, okay, 60.5 degrees. Then I could take that 60.5 degrees and that 60 degrees and give you something between that. And we can keep doing that exercise all day long, on and on and on, but you can never bottom out with that and reach or be able to identify the individual members of the set of reals. So that construct is called uncountably infinite. And because continuous random variables, their outputs are things that are real valued and things that are uncountably infinite, you can't use summation when you form these complex events. The only tool you have is integrals. Okay, and so when you construct these complex events out of real valued quantities that your random variables return, you're going to construct them. Yes, you can make a CDF to construct them, their probabilities, but you have to use the integral. Okay? All right. Any questions about this? No? All right. So we've talked about probabilities associated with individual random variables, but if you look in the world is not described by a single variable, right? This is particularly evident in computer vision. I mean, these are from pictures of Leipzig, Germany, and you know, if you're looking at pictures and in computer vision, you're computationally trying to characterize the content of images, things have color. There are all sorts of colors there. Things have shapes. If you look at this Mr. Clean Meister Proper bottle, you see straight edges, you see curved edges, you see this kind of hook. Things have texture, right? Variations of color over patches of image. Oh, oh, that's not good. Let me set this down here for a second. That's dangerous. Shouldn't even be in here. Okay, that's better. Thank you. So if we look at this image of this market, as you go across a scan line, whether it's horizontal, vertical, or at an arbitrary orientation, you see variability in the color with respect to space. And that's called a texture. So you see all sorts of things in images. And so when you're describing something in real terms in computer science, mechanically, as far as machine learning, computer vision, and AI is concerned, you don't just have a single variable. And in machine learning, a variable, same as a random variable, is the result of computing some sort of processing over your data source, right? So you can imagine processing that's going to give you descriptions about the color, processing that's going to give you descriptions about the shape, the orientation of the edges in the image, things that are going to give you information about the texture, right? So you have more than one variable that describes phenomena in the real world. And so these quantities, these outcomes of those measurements, they are in fact random variables. And in fact, in machine learning and AI, we use these random variables and we estimate their probabilities in order to do things like classification, clustering, this artificial synthesis of things. Has anyone ever heard of this term deep fakes? Deep fakes. A deep fake, for those of you who don't know, it's a video that looks realistic. So you'll see somebody, their likeness, and they're talking, and it's producing audio, but it's not the real person. And so what a deep fake is essentially a way of encoding a probability distribution and then sampling from it. And if you sample from it, you can produce things that look realistic and things that sound realistic, right? So this idea of using probability to describe these multiple variables that measure different aspects of your data, be that an image or video or what have you, is a very real thing. So we've only been talking at this juncture about single random variables, the number of heads in a coin flip, but you could certainly, for the same piece of data or raw event, imagine your raw event were an image, right? So any one of these images, that's the raw event. And then from this raw event, you can measure different things about it, like the color, the texture, the shape, and all sorts of statistics. So we have certainly multiple variables that we can have, random variables, and we put them together into a vector of random variables, also called a random vector. And so certainly if you think about images, the different things like colors, textures, shapes, and so forth that you see in images, those are not random, right? There's some structure. There are particular combinations of colors and textures and shapes that co-occur together, right? It's not random. Random looks like noise on a screen, just these dots that just dance around. But these are not random. And so if you can put together the distribution, now you can use that to do all sorts of interesting things. So let's introduce another definition. And this is in the book. And for this case, let's just assume we have two random variables, x and y. They're different x's and y's from the coin flip example. And x and y are random variables, and these represent a pair of measurements, a measurement over a raw event. X might be texture, y might be color, x might be shape. It doesn't matter what they are, but they're just two measurements over a raw event. So this is a vector of random variables, or a random vector, or two vector in this particular case. And this random vector has a distribution, because you can have a distribution of certain colors and certain textures co-occurring with one another, measured from the same image or even the same video. So we have a distribution, just like the distribution I showed you about the random variable that measured the number of heads in a coin flip. We can certainly have a distribution corresponding to a random vector of random variables. And so this is a so-called joint distribution. And these joint distributions talk about the coupling of information between these two random variables. It's not, excuse me, it's not always assumed that they're independent. Independence is something you have to demonstrate. So we have this random vector, and because they were derived from the same information source, let's say the same image, they're going to have some coupling with one another. One is going to influence the other. If we were to be able to compute the individual distributions of that first random variable x and that second random variable y, those one at a time distributions, those singular distributions, are called marginal distributions. And so part of what I will do today is talk a little bit about why it's a marginal and talk about how you get to that marginal distribution from this distribution over the random vector. Okay? All right. Any questions about this? Does that make sense? Yes. Okay. So let's go further into this definition. Now, as a probability, as a function, we could say the probability of value x, which is an outcome of random variable x, and co-occurring with value y, which is the outcome of random variable y, is equal to the probability that variables x and y take on values x and y. So here we have the function, here we have the random variables, and xy is the value that was observed for random variables x and y. And it's really important to note that the order matters. You say xy, not yx, and that it's a one-to-one correspondence between the value small x and the variable large x, as well as the value small y and the variable large y. Excuse me. So if you were going to describe it from the standpoint of something that looks like a Venn diagram, you'd say the probability that variable x takes on value little x, and at the same time, variable y takes on value little, that should be y. That's a typo, little y. Okay? So it's really important that and because they co-occur with one another, right? If you look back to these photos, right, you know that they look like apples over here, right? Apples have a round shape, and at the same time you see that round shape, you also see the colors like red, slightly green, and slightly yellow, right? In order to be an apple, those two measurements have to occur at the same time. So this and is really, really important to this description. So we have these values, and if we were to take a set of all possible values that x and y can take on, you can treat them as being mutually exclusive and collectively exhaustive. Collectively exhaustive means that all possible combinations are covered to represent the full set of appleness, if you will, if you're measuring the color and shape of fruit, and mutually exclusive, that one apple's color does not affect the other apple's color, right? So this idea of mutually exclusive, collectively exhaustive is really, really important, and we'll see that throughout the course of the semester. So the joint distribution then completely describes what's called the aboutness or the dataness, how this particular data behaves, if you will, right? So you don't see purple apples. Maybe at some point with some genetic engineering or what have you, you might see purple apples, but you only see certain colors associated with certain shapes for an apple. Some apples might be elongated or more oblong. Other apples might be closer to being round like a sphere. But you don't see a weird apple that's shaped like a banana, right? You just don't see it. So it's absolutely true that if you can find this joint distribution, you have a complete description of what it means to be an apple, for example, as it pertains to those measurements, x and y, your two random variables. Okay. Any questions about this? Does that make sense? All right. And if time permits this semester, see how it goes. Maybe I'll throw in a little bit of machine learning, depending on a whole host of things. Okay. So let's give a framing example. Suppose you have a fair coin and you have a fair die, and you're going to roll this, flip a coin, and you're going to roll this die, right? We all know at this juncture that the outcomes of a coin flip are heads and tails, and so we're going to list that along the top of the table. There's our heads, and there's our tails. And likewise, the outcomes of a die are 1 through 6, so there's our 1, 2, 3, 4, 5, and 6. Okay, so if this is a joint distribution, we're saying a coin flip and at the same time a die roll. So you can imagine you put the coin and the die in your hand, you kind of, shook your hand a little bit, and you just threw them both on a table, right? You're going to have a joint distribution that describes these. Now, certainly, we know at this juncture, it's a one half probability associated with the outcomes of a fair coin, and it's a 1 through 6 probability of each of the sides of the die. Now, because these two don't impact the outcome of the other, right? But these events co-occur, we're going to write them out together and multiply to fill in the value of the probability for each one of these cells. So let's take this first cell. We have the coin is equal to heads, and we have the die is equal to 1. Well, it's a 1/2 probability for the coin being heads, and it's a 1/6 probability for the die being a 1. So we multiply the 1/2 by the 1/6, and we get 1/12. And we do that for all of these combinations, completely filling in every entry in this so-called joint probability table. And so now we have 1/12 for each one of them. And of course, if you biased the coin or biased the die, you milled it so that it wasn't 50-50, or you milled the die so that each outcome was not 1/6, you would certainly have different entries in this table, right? So this is our joint probability table. Any questions about this? No? Okay. So one of the things you might want to know is like, okay, well, I know I'm rolling the coin, rolling the die and flipping the coin at the same time. And this is joint distribution that describes the behavior of the co-occurrence of these observations together, right? But you might want to know one of them, given the fact that you have this joint distribution. So let's think about, what if we want not the probability of the coin flip and the die co-occurring, but what if we wanted just information about the coin flip, or just information about the die, but what we get are these joint observations. So you get a set of observations. So let's say the coin flip said heads, the die roll said 1. The next observation, the coin flip said heads, the die roll said 3. And let's say the next observation, the coin flip said tails, and let's say the die roll said 5, for example, right? So you're observing a set of vectors of values, and given those values, you might want to know, well, what's the probability of the coin flip, even though I get this vector of observations? Okay, so what you're doing to do this is something called marginalization. And what it says, and let's focus on the coin flip at the outset. Suppose you wanted to know the number of the probability associated with the coin flip alone. But confounding you is the fact that you have these vectors. So the first thing you do is you think about, okay, well, let's look at this table. And we know the coin flip can take on a heads in the left-hand column, or tails on the right-hand column. So the question you ask yourself is, okay, let's consider how many ways a coin flip can take on a value of heads, given all of these joint occurrences that can happen. Well, let's see. We can have a heads with a 1, right? That's this one. You can have a heads co-occurring with a 2 for the die. You can have a heads co-occurring with a 3, a heads co-occurring with a 4, a heads and a 5, and a heads and a 6. Now, if you want to compute the probability of a coin flip, you have to account for all of those 6 many possibilities of the die that could kind of come along at the same time, because it co-occurs with the coin flip. So how you do this is you add up all of these components, because the coin flip can occur 6 different ways alongside the 1, 2, 3, 4, 5, or 6 outcome. You have to add up all of those if you want to know what the probability is for the coin being heads, because there are many different ways it can be heads. Okay, so if we do this, we get 1/12 plus 1/12 plus 1/12 6 many times, which is 6/12, which is equal to 1/2, right? And there's our 1/2. Likewise, if you wanted to know the probability of the coin flip being tails, you could do it one of 2 ways. You could sum for all of the ways coin flip can be tails. So you can have tails in a 1, and a 2, 3, 4, 5, and 6. You could sum these, so it's 6 many times. You're summing together 1 upon 12, which is 6/12, which is also a half. You could make the observation that I know my probability of coin is heads is 1/2, and I only have two states for the coin, heads or tails. So you can use the law of total probability to just say 1 minus the probability of the coin being heads, which is just 1 minus 1/2, which is also equal to 1/2. And the important part here is that you're making use of these laws, right? Don't just write the answer when you're doing problems like this. It's important to state why. By law of total probability, I can do this. Okay? All right. Any questions about this? Make sense? So we have a joint distribution, and now from that joint distribution, we can compute the probability of a single variable. And this is the case if it's two variables in the vector, if it's three variables, if it's k variables, doesn't matter. You just keep doing this summing. Granted, it gets more complex, more computationally complex, the more variables you have, but theoretically, it's entirely possible. Right? There are other techniques that are used in practice that are beyond the scope of this class. So you'll notice here, if you think about this table, the fact that we sum down, these columns kind of look like margins on a paper, right? All the numbers are flush with one another, and we're going down a column. And in fact, this procedure is called marginalization, right? And so this idea of summing out all of the contributions for the variable that you do not want for these co-occurring values in order to arrive upon a probability involving a single desired variable, that procedure is called marginalization. So let's take a look at this. Suppose we have two random variables, x and y, and we want the probability of x, right? This expression up top. So that's the probability that random variable returns value little x. We sum, and we sum over all the values of y, whatever that joint distribution is for those two variables, x and y. In this particular case, we said the probability that the coin equals some value c is equal to the sum for all the dice values d for probability of coin, comma, die, right? That's exactly what we did visually in this table. Okay. Any questions? Does that make sense? Yes? Okay. So, you can do the same with the first variable, with the second variable, and in this expression down below, I'm just doing it with y. So in this case, I'm summing over all the x values in order to get the marginal distribution for the probability of y. Okay. All right. So, of course, we can do it the other way. Suppose we wanted the probability of the die roll, probability of die. We just sum out for all the coin values, probability of coin, comma, die, right? And that's exactly what we're doing. In this case, we're summing across the margin instead of down the margin. And so here we have 1/12 for each value. And say a die roll of 1, this occurs with heads and occurs with tails. So we sum them together. 1/12 plus 1/12 is 2/12. That's 1/6. That's exactly the probability of the one outcome for a die only. Okay? And so in similar fashion, we can do that same procedure of marginalization for the die roll outcome is 2, 3, 4, 5, or 6. We sum along this margin, and this procedure is called marginalization. Okay? All right. Any questions about that? No questions? No? All right. So we can do this either down or across. This procedure is called marginalization, and I'm only showing a 2-vector here, but this works equally well with a 3-vector, a 4-vector, a vector of arbitrary, a random vector of arbitrary dimension. Okay. So independence. Definition-wise, we talked about independence in terms of conditional probability, that if two variables are independent, conditioning on one does not change the probability of the other. Another definition for independence relates the joint distribution of a random vector to the so-called marginal distribution. If we have two variables, random variables, big X and big Y, and big X and big Y are independent from one another, it means the probability of the joint distribution, the left-hand side of this expression, is equal to the product of the marginal distributions. So here we have P of X and Y, and on the right-hand side of equality, we have the probability of X times the probability of Y, right? That is another definition for what it means for two variables, random variables in this case, to be independent from one another. Okay, questions? No? All right. So this ends, bless you, the module, and we'll pick up with MATLAB, and we still have a fair amount of time. And if we don't finish what I have to do, wanted to show in MATLAB today, we'll certainly pick up with the balance of it on Tuesday. Okay. All right, so let me bring up MATLAB, and we will look at how you might write MATLAB code to implement this idea of a conditional probability. So let me start MATLAB. Let me get my mouse. Okay. So in the interest of time, instead of typing it in front of you, I pre-populated a MATLAB file, and it's called cardgame.m. And I can certainly post this on the Blackboard alongside the module for Lecture 6. Okay, so we have a deck of cards here. And this deck of cards is a full deck of 52 cards. And the way I encode these cards is I have the first two characters in a string. And the first character represents the card value. I'll call it value. And so A stands for ace. Excuse me. K stands for king. Q stands for queen. J is for jack. 10 is just the 10 card. Then we have 9, 8, 7, 6, 5, 4, 3, 2. And then the second character, H, that stands for the second character rather, stands for the suit. So we have four different suits. We have hearts, diamonds, clubs, and spade. And so H, lowercase h, stands for heart. So AH would mean the ace of hearts. D stands for diamond. So AD would stand for ace of diamonds. C stands for clubs. So AC stands for ace of clubs. And S stands for spades. So AS stands for ace of spades. Okay. Now, this is the way I chose to do it. You could use other constructs that we can mention in another sitting, but I chose this just because it looks nice and it's easy to tell what's going on. Okay, in practice, I would implement it as a structure and have two different elements of the structure, one for the value and one for the suit. But that's neither here nor there. We can talk about that at the right time. All right, so we have an entire deck of cards, and I'm going to write a function that's called filter given, right? And recall when we talked about what a conditional probability is, we motivated it with the example of having multiple attributes associated with tennis balls. And to draw your memory, those tennis balls could either have a color attribute, uh, which was red, I'm sorry, which was yellow or green, and they could also have a bin number written on them. And you can imagine, in black magic marker, writing a bin number on it, and that was 1, 3, 5, or 7, right? So in this particular in that example, when we said probability of getting a green tennis ball or yellow tennis ball, given that I know that they were poured into the bag from bin 5, right? That given acted like a filter, and what that given did is said, okay, well, I'm going to go through my universe of consideration, and I'm going to remove from consideration those elements that do not match what was given. So in the case of those tennis balls, you took out all of those balls from consideration that did not have a 5 bin number written on them with black magic marker. Then for what remains after you do that filtering, you then compute the probability of those desirable balls, the ones that are yellow, and your universe of consideration has now changed. It's no longer all the tennis balls, it's only the number of tennis balls in that case that were from bin 5 and thus had a black magic marker written on them. So in the case of something like a poker game, you can imagine and we'll assume we have a single deck of cards, but you can imagine that you observe the dealer put a card in front of someone, and let's just assume, and I can't remember which version of poker, you have a card that's put face up, and everyone can see that. So if you see that a certain card was given, now that's new information, and you're going to filter your universe of consideration and then compute your probabilities accordingly. So, let's imagine that, you saw that a king, a king of hearts, an ace of hearts, and a queen of hearts were dealt out, right? Then, if you wanted to know the probability of getting a king, right? Given that those were already handed out, you're gonna do that filtering first, and then compute your probabilities from what remains. Does that make sense? Okay. So what we're enterprising to do, and I'll just write it as a comment here, so that we'll remember what we're after, is to be able to compute, for example, the probability that I can get a king in any suit. I'll say king underscore, as if it's a wild card, given, let's say that I knew the ace of hearts, the king of hearts, and the queen of hearts were dealt out, right? And that's exactly what we want to be able to compute. And we're going to do it by this filtering. All right. So we have what is given, and we're going to use a cell array to connote that. And then, of course, to compute the probability of king, we're going to have to do some string operations, and we're going to sift through uh, an altered version of the deck of cards, and we're going to look at that first character to see how many of them have a king, right? Make sense? Yes? All right. So the first thing I'm going to do is write a filtering routine, and this is going to be a simple one, and we can modify this um, depending on how long this takes over time. So I call it filter given because it's going to perform filtering on the deck um, when you're given a certain condition. Right? That's just what I chose to call it. You could call it something else. This note is just to myself. I want to remember how to do something, so I write notes to myself beforehand. All right. So filter given is going to take two parameters, and this is filter given. It's going to take our sample space omega. I'm going to call that local variable omega our universe of consideration. And that universe of consideration is going to be the entire deck of cards. Or if it's an altered universe of consideration, you can input that if you want to implement a further condition. And then the second parameter I'm calling givens. And givens is the set of cards that were observed. So, for example, in card game, I say filter given, it returns back an answer, and the universe of consideration is the deck, and that was the deck, the same deck that's up there. And the givens are the king of hearts, the ace of hearts, and the queen of hearts. And so here, I'm trying to implement that filtering function corresponding to the condition here, what's given for that probability. So this expression up above, P of K underscore given AH, KH, QH, that's mathematical, or mathematical expression. But in order to compute the new universe of consideration, the result of this, what's given, I'm going to do this filtering, and this filter given is the routine that I've chosen to call it that's going to perform that altering the universe of consideration. Does that make sense? Okay. So let's look at filter given, and I know what I want to do, and then we'll talk about how you can implement that in MATLAB. So what I want to do is when I am presented a list of what is given, I want to take my cell array, and this data structure is a cell array, of the unadulterated deck of cards, and I want to loop through it, and I want to find in this list, AH, KH, QH, I want to find where in this cell array called deck, where does each one of these list items fall, right? In what position? And so I'm going to use MATLAB built-in functions to help me do that. Okay, and so it just so happens that IsMember is a routine that'll allow you to do that, right? So if we type help IsMember, and how you would find something like this, you bring up your trusty browser, Google is your friend. How do I find the contents of a cell array in another cell array in MATLAB, right? As easy as that. Okay, and so I really want to empower everybody to be able to, you know, fend for yourself, right? Learn to fish, not be given a fish, right? You want to be able to go out and find this information for yourself. And so, if you poke around a few of this results, you're going to find this routine, right? And people will have all sorts of other implementations, and it is not incorrect to implement it yourself. You could absolutely implement a loop, a nested loop, where for each item in what is given, you're going to loop through the entire cell array, and you're going to pick out things that match and then put them somewhere else. You're absolutely correct in doing that. But using the MATLAB built-in functions will make things a lot quicker and easier for you. But it's not incorrect to write it yourself. Okay, so if we look at IsMember and we look at the help associated with it, the manual, I'm not manual pages, the help pages, I'm in Stochastic, not operating systems. And we look at IsMember, right? And we see that IsMember for arrays A and B returns an array of the same size containing true where the elements of A are in B. Okay, so it'll mark positionally, but it'll also give the index number, and that's this version down here, the third version, IsMember AB, when you have this thing called a multi-return type. In MATLAB, when you have a return value, unlike C and Java, you can return a list of things instead of just a single thing. And this version of IsMember that returns two items in a list, excuse me, will also not only look at where it is in the origin, but also the index in the second array where it's located. And we'll take a look at that, tinker with it a little bit, convince ourselves that it does work. So let's try it. So we're going to call IsMember, clear, CLC. And let's say we have two cell arrays. We have array A, and let's say array A has the number 1, 3, 1 and 3, just to make it easy. It'll only have 2 in there. And let's say we have a cell array, 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 array B, right? And let's say B has all the numbers from 1 to 10. 1, 2, and this is a cell array of strings. 2, 3, 4, 5. Let's cut it off at 8. I don't want to type all that. 6, 7, 8, for example. Okay. So now we say array A. Yep, it's there. It's a 1 by 2, right? You can check the contents in the workspace, right? If you go inside the cell array, the first item is 1, second item is 3. So it's there, it's alive, and all that good stuff. If we were to take the size of array A, it would give us those dimensions, 1 by 2. If we were to take the length, another built-in command of array A, it's going to return back the number of items in that dimension that is larger. So in array A, it's 1 row by 2 columns, and so it's going to return back 2 if you say length, but size is going to return back in the first position the number of rows, in the second position the number of columns. So it's a 1 by 2 matrix, which is just a vector. Okay, so likewise, if we looked at the size at array B, ARRB, right, you'll notice it's 1 by 8. And if we took the size, right, of array B, it's 1 by 8. Now, if we wanted to use this multi-return type, we'll just kind of demonstrate that here in the command window. I could say the number of rows in B and the number of columns in B is equal to the result of size of array B, right? So if I do that, what MATLAB does, we know that when we take size, it returns the number of rows and columns. It's not just rows and columns. If you had 3 dimensions, it would return back the rows, columns, and the depth. But in this case, because we only have 2 dimensions, it returns back first the rows and secondly the number of columns. So when we do this multi-assignment, the first position in this array of variables is going to get the 1, and the second position in this variable here, it happens to be cols B, is going to get the 8. So if we look at rows B, it's a 1. If we look at calls B, it's an 8. And you can also see in the memory window where it created the storage to represent those variables. Okay. Any questions about this? No? Okay. All right. So that's the multi-return type. And if we type length, right? Length, length for rows B is going to return back an 8. Oops. Oh, it's array B. My mistake. ARRB. There we go. It's of size 8. Okay? All right. So that's a multi-return type. So if we use isMember, right? Let me go back to that help page. Help isMember. IsMember, the version that does the multi-return type, is going to give us two things. It's calling it LIA, the location in A, and location B in B. So it returns an array, location B, containing the lowest absolute index in B for each element in A. So basically, it's going to return you the indices. So now, let's try this out with what we, oh, you know what? I just cleared memory, CLC. I'm going to have to recreate them. So array A, and let's recreate array B. Okay, so let me call um, location in A, location of B, and I'm going to say isMember array A, array B. Okay, so if I type LOB, LOB, it says in position 1 and position 3 of B, that's where I'm going to find the elements of array A. Okay, so let's check. Array A has a 1, all right, that first one. Yep, it is in position 1 of array B. And then the 3, it's in position 1, 2, 3 of array B. So yeah, it seems to be working. So what we're going to do then is when we have our givens, we're going to use isMember to check where in our sample space omega each one of those given cards occurs, and then we're going to delete them. Right? We're going to modify that universe of consideration, and when we delete them, we're going to save them and return back the result. But then we're also going to take our omega and we're going to change our universe of consideration. Okay? All right. So let's do that. So now that we're convinced it works, we'll go back to filter givens, and I'm going to uncomment this. And what I'm going to do is I'm going to look at all of the positions. I call those hits, the location. And then this other variable I'm not going to use. That's just location in A. If I actually want to see what it looked like in that example, it says, yep, it's true that I found an instance of the first element of A somewhere in B. And it's also true, one, it's a logical array, that there's a match for 3. So what this multi-return type for isMember does, that first return gives you a true false. Did I find it somewhere or did I not find it? A 1 means true and a 0 means false. So what it means here, it's true that this 1 exists somewhere in B. Now it would say 0 if you entered something that didn't exist. It's true that the 3 occurred somewhere in B. If I were to take this A and I were to change it, so let's say 1, 9, and the 9 does not occur in our B array, when I try this routine again, if I look at LIA, you'll notice there's a 0 in the second position. So what that 1 represents is, yep, 1 occurs somewhere in array B. 9 does not occur anywhere in array B. So it says it is false, right? That this 9 is somewhere in B. Okay? Make sense? Okay. So I'm going to call isMember, and I'm going to use hits, which will contain the indices into our sample space omega, the deck of cards, and it'll tell me where in that deck of cards I find everything that was given. Make sense? Yes? Okay. So I'm going to try that out, and let me set a breakpoint. Let me save and just show you, yes, it really does work. And let's go back to card game, and let's set a breakpoint here. Let me run, and I'm going to step into this function because I want to show you, well, that's my deck of cards, and you notice a 1 by 52 cell array, right? There are 52 cards in the deck, all right? And if I look at my givens, there's my king of hearts, ace of hearts, queen of spades. Okay? All right. So now let me step the number of givens and the number of observations I have in my sample space omega. So the givens are 3 many, okay, size 3, and 52 for the number of cards. So let me call this routine IsMember. And if I look at the positions, it found something for each of them. So it found the king of hearts in omega. It found the ace of hearts in omega. It found the queen of spades in omega. Well, obviously they're cards, but if I gave it a card that doesn't exist, especially after I modified our sample space as a result of filtering, then it would be returning 0 for that position. If I look at hits, I see that in the second position of omega, I find the the king of hearts. In the first position, I find the ace of hearts. And in the 42nd position, I find the queen of spades, right? And I'm not going to do that. I could actually verify. So if I go to my omega, and I say, all right, give me back the first position, that's ace of hearts. Give me the second position, that's king of hearts, and give me the 42nd position, right? That's queen of spades, right? So yeah, it's working how we want it to work. Any questions about that? No? Okay. So now that we are given this, what I want to do is now change my sample space omega and then send the result. And remember, when we're given something, we're removing it from consideration, right? We're changing our universe of consideration. So I'm gonna say new universe, new omega, right, is going to equal something, right? And what is that something going to equal? Well, the first thing I want to do is I want to take my hits and I want to set that position of the cell array to null, right? And how I set it to null, if memory serves me, let's see. Um, B array B position 1 equals open close brace. Oh, I had removed it. Okay. Array B equals 1, 2. So I'm going to test it out. 3, 3. Okay. Array B. This is my cell array. Now, if I said set the second position of array B to be null. Now, if I say array B, now you'll notice here that second thing is gone, right? And so how I remove something out of a cell array is by setting that particular position to be this null character, this null array element. So I know what my hits are, and the hits refer to indices. So now I'm going to say new omega is equal to the result of omega setting the value identified by hits to be empty. So let's see if that works. So let me say new equals array B. So let me try that. Omega hits. Let's just identify omega hits. Omega hits works. And if I say omega hits equals null, omega hits, it's changed, so that means it's removed it. Okay, that seems to be working. All right, great. So let's do that. So we take omega hits. Hits says, give me the indices that I just found using IsMember, and I'm going to retrieve from omega those elements found at indices 2, 1, and 42, and then I'm going to take them and I'm going to replace them with empty, right? Okay, does that make sense? Any questions? All right, so now that's my omega, and I'm going to say result equals omega. All right, quit. Let me save that. So now let me go back to card game, and answer is going to be the return value that is the result of striking from consideration those givens that are specified in the function call. Does that make sense? Any questions? All right. So let's save this and let's run. All right. So again, I step in. I see that step, I get the length, I get my hits. In this case, it's 2, 142. I change my omega. So let me bring up omega. And my omega, you'll see I have 52 elements. And position 1 is ace of hearts, 2 is king of hearts, and 42 is queen of spades. 42 is queen of spades, right? So now I'm going to, let me get that away. So I'm going to increment there, right? So let's look back at the omega, see how it's changed. You'll notice a 1 by 49 cell array. I've removed 3 things from the cell array. If we look, well, the king of hearts and the ace of hearts are no longer there. What I'm left with is the queen of hearts. And of course, in position 42, that's also changed. The queen of spades is gone, and everything is sort of moved over. And you'll notice I only have 49 cards now that I've removed 3 cards from my deck. Does that make sense? Questions? All right. So that's my new omega, and I can even verify uh, length of omega after I remove all of the hits. Length of omega is 49 and no longer 52. So then I step, return the result, and accept the result. And now I have a new version of my sample space in variable answer that is the altered version of my original universe of consideration. Okay? Questions? All right. So now that's my filtering based on specific cards that are given. And I have that as a function. So now what remains, let's say if I wanted to know the probability of a king or the probability of a queen or any sort of card value, I want a different routine now that's going to tell me how do I do this matching of k underscore, meaning k followed by anything or q followed by anything. And what I'm going to use to do that is look at the first character in each string or do a string compare or string search to see if the k is inside of any of these strings. And the reason why I'm going to do the string compare instead of the first character, because for some of these cards, I have 2 digits. I have a 10, right? And it would sort of confound things if I only assumed that everything was a single digit. So let me ask Google, and how do I search for a string in another string in MATLAB? There we go, as easy as that. So find strings within other strings. It's the first search result. So it's string find. So how does string find work if you're doing this yourself? You have a string, that's the string you're going to search within, and then you have a pattern, it's what you're interested in. So I'm going to do string find, give it the string, and then the pattern I'm looking for. So if I wanted to search for a king, right, let's say a string 1 is equal to king of hearts, right? And let's say pattern 1 is equal to K for king, right? I would do str, I think it was str find, str find within string 1 the pattern pat1, which just happens to be K. Yep, it occurs, and it occurs in the first character. So what if I did, let's say string 1, let's test this out. Let's say it says Q, H, right? And let's rerun this find, empty, right? It's nothing. So you can't find it if it's empty. It doesn't have it. Okay, so we know this str find works, and we're going to use that now to do this other filtering about counting the favorables, right? Okay, so what are we going to do? Let's create a new routine, and now we're going to say count favorables. And count favorables is going to return back a number, so I'm going to call it a function, return val, you could call it return value, whatever you want, is equal to count favorables. So count favorables, equals count favorables. What did I do? Result. Let me just call it result. Count favorables is going to take two things. It's going to take a cell array, right? That's a universe of consideration, and then it's going to also take a card value, okay? And what it's going to do is it's going to count the number of times that card value occurs in the universe of consideration. And each element in the universe of consideration is going to be a string, okay? Like AH or QS or what have you. So I'm going to do a little bookkeeping and say num universe size is equal to the length of the universe, right? That's the number of elements or the cardinality of the universe of consideration. And now I'm going to have a loop, um, or I could just say find. Um, I'll do a loop. Num uh, num hits is equal to 0, starts out as 0, for I goes from 1 by 1 up to universe size, end. So I create the block, and now I'm going to say if, let me see what string find returns. String find returns an empty array. If is empty. So let's see. I think I had that out here. Is empty. Okay. All right. Is empty. If is empty, if it's true that it's empty, when I do an str find of within universe the ith item, so I'm going to each of the each item in the universe of consideration, and I'm doing a string find uh, within that of the card value, right? And if that result is empty, if it's not empty, meaning that I have a hit, then I'm going to increment card val. If not is empty, oh, it's asking me to use contains. Yeah, that's fine. If contains, contains. So let me look for the help contains. So contains says true if it's found, if pattern is found in text. Okay, that's a better one. So if contains, if card val is in each of those elements in the universe of consideration, then num hits gets num hits plus 1. So increment num hits. Okay, so let's test that out and see how we do. Count favorables. Let me save that. So let me go into card game. I'm going to filter the deck, and this is going to be our modified universe. Modified universe. Universe. The result of filtering. And then I'm going to say, oh, you know what? I didn't return. So we're going to say result is equal to num hits. I want to use what I've counted. All right, so now I'll go back to card game. I modify my universe of consideration, which starts out as the deck, and then I say num favorables is equal to count favorables, right? I'm going to use the modified universe, and then the card value, I'm going to say K for king. All right, so capital K for king, and there we go. Okay, so once I get the number of favorables, I know the size of my modified universe, right? So num size mod universe is equal to length of mod universe, okay? And then we say probability is equal to num favorables over size of the modified universe. Okay, all right, that's a bit of a mouthful. Any questions so far? So I'm literally computing the number of favorables, that's 112, over the modified size of the universe. So let's run this, and I'll certainly pick up with this on Tuesday. So let's step in, and we already know that that works, so let's continue. And we'll run to step out, so run to the function return. And so this is our modified universe. And now let's go inside of count favorables. And if I don't have a bug here, so the universe is modified. That's 49, right? The card val I'm looking for is king. And so let's just continue. And num hits should be 3. Num hits is 3 because there are 3 kings left if our universe has been modified by removing one of the kings. And so let's continue, step out. Oops, where was it? Line 23. Num hits, line 23. Num favorables. Undefined function, num hits. Let me clear this. Let's see. Clear, CLC, save. Let me run this. Continue, continue. Result equals num hits. Oh, hum hits. All right, num hits. All right, there we go. Spelling error. All right, so let me save. Let me run this, and we'll end with that. So let me run, continue. Let me remove that breakpoint. Let me step out. Step, step. Return our result. And we have modified universe. We have num favorables. So we take the size of the modified universe, that should be 49, and we compute our probability. And there's our probability 0.0612, which is 3 over 49. Okay? All right, so there we have it. That's an example of how you would implement conditional probability. It's nothing more than a filtering probability. And we will carry this example a little forward and make use of it probably after midterms, which is coming up, I think, the week of the 30th. And we'll talk about midterms on Tuesday. All righty? Okay. I will see you on